Okay, very good morning to everyone. I hope you can hear me clearly and can see the screen also clearly.
Yes, sir. Good morning.
Okay, thank you so much and a very good morning to you too.
Good morning, sir.
Good morning to you too. Okay, so yesterday we finished this topic on salinometer, a device that is supposed to check how saline the water is. That means we are generally wanting as fresh water as possible. And that's the two places where we are wanting as fresh as possible is your freshwater generator and your cascade tank for your boiler. Okay. So what is the principle of it working? As we saw, even in the ICCP system, it is the seawater. Okay. Where the seawater as compared to fresh water conducts more electricity than fresh water. So using that principle, a particular cell is inserted into that particular line, okay, whereby whatever the water is going to flow, and that cell, that water is going to flow through this cell, okay, and depending if the salinity is higher, it will conduct more electrons or more electricity between the two plates of the cell, and by conducting more electricity means the current is going to increase in the system. And by increasing in the system, it is correspondingly going to activate these current operated relays. They are not voltage operated relays. You can see it straight away from the simple fact that they are in series. If they are going to be in series, they are going to be current operated relays. So because of the increased current flow, the respective 1 and 2 are going to get energized. One giving, number 2 giving the alarm, and number 1, which is going to short out the display. So most of the time, whenever you're going to get high salinity alarm, you will be having the display, which is going to be blanked out. It's not, you won't be able to make out. Okay, so by that very fact that it is blanked out, it means it's a high salinity alarm. Then we saw that salinity also, remember when we were doing the ICCP, okay, we saw that the protection current, how it is going to vary. It will vary with the size of the ship. It will be varying with the speed of the ship. One of the other factors was temperature of the seawater. Okay, so obviously seawater temperature is going to have an effect on the conduction of this current. And that means when the temperature increases, so also the current is going to increase. So therefore, they have a temperature compensator. And as the temperature is increasing, this particular resistance is shorted out, allowing for more current to pass through here. Yes, it is going to pass through this thing, but it is acting as a bypass to this circuit. And this circuit is basically your alarm circuit. So you are avoiding unnecessary alarms. Also, this is acting as a extra protection towards the movement over here for this particular meter. Okay, but the prime reason this temperature compensator is used is so that you don't get unnecessary alarms. The extra current that is going to be extra current due to the conductivity nature of your seawater, again due to high temperature, that conductivity, that extra current will be bypassed through this. As the temperature rises, this particular resistance is going to be shorted out. Now, as I said, this is a very, very, very basic circuit diagram. Okay, so what we have been finding is that they are basing all their questions on these very basic diagrams that we are presenting to you. So practice this diagram. It's a very, very simple diagram to draw. And once it's stuck in your head, there is absolutely no way that you can make a mistake. Okay? Right. So this is what we concluded yesterday. So any queries or doubts on the salinity or salinometer? Okay, so let's see a video on this very one. Okay, so let's see the salinity indicator video.
The topic for today is salinity indicator. Salinity is saltness or the amount of salt dissolved in the body of water. And salinity is an important factor in determining physical characteristics like the density and heat capacity of the water. In common, it also determines whether the water is fit for human use or not. And this is a picture of the salinity meter. The salinity indicator or the salinometer is an instrument to measure the salinity of water. It uses the property of electrical conductivity of water or liquids. The principle is built on the electrical conductivity of water. In case of pure water, the amount of salt content is very less, but seawater, on the other hand, contains lots of impurities such as sodium chloride, magnesium chloride, etc. The chloride ion helps in conduction and helps these impurities increase the conductivity of water. And coming to the working part, there should be electrical supply, and the electric supply must be DC. And another point is that pure water is non-conducting, so that current flow is an indication of impurities. That is, the greater the current, greater the impurity in water. Now, this is the electrical diagram of the salinometer. We can see that there is a pilot lamp, and this is a water sampling cell, it's a potentiometer, and this is a temperature compensator, and this is the alarm. Number 1 and 2 are the two relays, and this is the ammeter. Basically, it measures the current, and more current means more impurities. Basically, this measures the impurities of the water of the sample. And the working is like when the impurity content in this water sampling cell exceeds a fixed value, the current is sufficient to operate relay number 2, this one, and closing the switch and will give out alarm. And also the current will pass through this way into this millimeter ammeter, and it will show the reading. And there is a problem when the continued operation of the current, of the increased current, will damage the sensitive millimeter. So what happens is that if the current is more, relay 1 will get activated and it will bypass this ammeter. So alarm will be working, but this ammeter won't be working since it will be bypassed. So it is for relay number 1 is for protection. And there is a temperature compensator. We know that water temperature increases conductivity, so that the temperature compensation is required. A temperature compensating device, basically a thermometer, is shunt across the meter and protects it. See, it is in parallel to this meter. And what happens in the temperature compensator is that the temperature increase causes a rise in mercury level and cutting out of resistance, which allows more current inside to the temperature compensator and less current to the ammeter, so that it doesn't damage this ammeter. And salinometer is mainly used on board in a freshwater generator and in boiler to know the amount of salt content. It will be in parts per million ppm. It will be displayed on, in case of freshwater generator, it will be displayed on the local panel, and in case of the boiler, it will be displayed on the local panel as well as the ECL.
Okay, so any queries or doubts on your salinometer? Okay, so we will now move on to what is shaft earthing. And next week, we will be also doing MGPS, although last week we said we won't do it. I said I will postpone it for later, okay? And when any topic is repeated, treat that as a revision topic. So any questions that I ask, since Ankit sir has already taken up the topic, you should be able to answer. So at that particular time, you treat me as the examiner. Okay. So you should be able to give your answer. And like this, many times, some of our topics are repeated. So whenever I've done it before, Ankit sir, and Ankit sir is going to do that topic and he asks you questions. You should be able to answer it without blinking your eyes. Okay, it should be so quick that you are able to answer. Okay, 2-3 times if you sit and you get these topics thrown back at you, you become more and more proficient as far as answering your the orals is concerned. Okay, right. So shaft earthing. If they touch on this topic, okay, very first question that is asked to you is, why is shaft earthing required? Okay, why is shaft earthing required? And you can see that the answer here is, the very first thing is to avoid your main bearing. Main bearing means the main bearing of your main engine. Engineers know. Okay, so that's why you're doing your crankcase deflections and all that, no, for your main engine. Okay, you are taking the gaps also between your the upper and the lower bearings of your the rotary movement. How is the rotary movement got for your shaft? It is the up and down piston movement, that is the vertical movement, okay, is then converted into a rotary movement by means of this piston and your bearings, okay, which are connected to your shaft. Okay, whenever the electrical officers and whenever you're going to see them doing it, just have a look. No harm in having a peep to see how it is looking like. Okay. Now, these main engine bearings are very, very critical. When you are saying critical, most certainly it has everything to do with a lot of safety. Number one, if that thing gets pitted, the bearing gets pitted. Why pitting happens is because sparks or arcs, we saw in a high voltage thing, arcing is created. We saw in our ACB, arcing is created. That means certain metallic contacts are away from each other. That means here the main bearing and your shaft are away from each other. But the gap is so close that any buildup of electricity will arc across. Okay, will arc across, and whenever you're going to have an arcing, there is heat developed, and because of the heat developed, it is hot spots. Hot spots being performed or being formed. Where are we? We are in an enclosed space that is having your lube oil and lube oil mist. Okay, mist not to such an extent that during normal operation this is almost negligible. But if this hotspot occurs, then you are going to create such a lot of mist that first and foremost, your OMD, oil mist detector, would detect that in that particular crankcase and give the alarm. Okay, normally it is around 15 ppm thereabouts, between 10 and I think it is 10 ppm, not 15. 10 ppm, anything 10 ppm and above, you get the alarm, and then you get the automatic main engine slowdown if that alarm does not get mitigated within a certain period of time. Okay, and then once the main engine slows down, why is the main engine slow down? So that much of heat is not generated. You're going at full nav full, isn't it? So the friction that is going to be caused and the amount of heat because of that, the hotspot is going to be hotter than normal. Okay, but then when it is given to slow ahead, okay, then it's not going to be generating that much of heat, and you're going to avoid a major catastrophe in the form of a crankcase explosion. It could lead to that. Okay, so first and foremost, to avoid the main bearings of your main engine from getting pitted. Okay, number two, by avoiding this pitting, remember, whenever pitting is occurring, there is a formation of carbon. That's number one. Number two, also your bearing, which is commonly called white metal, if you have ever heard the term. that gets worn out and gets into your particular main engine lube oil. Okay, that is why you have your main engine lube oil filters. You will find if there is this problem of the spitting, etc., you will find that the white metal has gone in. Your naked eye will not be able to see it. But those filters are they are having such a fine micron capability that these very, very fine particles cannot pass through that. It is less than 1 micron. 1 micron is a very, very tiny particle. And then what is going to happen in your backwash filters? Those filters are going to get choked and you're going to get the alarm again and again, which is a very clear indication that now your particular main engine lube oil, whatever is there in your sump, has got badly contaminated. That is why quite often, I think it is on a 6-monthly basis, if not more, but minimum 6-monthly basis, your main engine lube oil from your sump, mind you, not from your main lube oil tank. It is not circulated back. Excuse me, guys. It's not circulated back to the main engine, main lube oil tank. That is pure oil. Whenever the oil diminishes, then oil is transferred from your main lube oil tank to your main engine sump. Okay, so a sample is drawn from your main lube oil that is being consumed and sent a show for analysis. Okay, and then if they'll come back with a report, and when they say the cat finds or the white metal is very high, that means something is wrong with your main engine. Okay, so generally, if it comes as white metal very high, then company would tell the chief engineer just investigate the reason why. Okay, so it can lead to a very, very big problem. I remember on one of my ships it happened. Okay, for some reason they had this thing. It was very critical in the sense that it almost came to a crankcase explosion. Luckily, they did not. And they could not run it happened on 2 main engine bearings, all because of this shaft earthing. Okay, 2 main engine bearings when we were somewhere between the Philippines, we were going to Baoxing or some place in China, okay, which is quite near to Hong Kong. But to cover a distance of approximately 1.5 days, it took us 4 days. We literally limped into port, and then after discharging, we were put to a lay berth, and then it took a week because they got the technicians, they had to grind the thing and see, and there was a lot of hangama, Not to talk about the cost of getting that thing back into shape so that you could run your main engine normally. Okay, so why is shaft earthing required? To avoid main engine bearing pitting, and by preventing the pitting, we prevent degradation of your main engine lube oil. Okay. Now, how is this electricity generated? The one that is going to cause the main engine pitting. Okay, by the way, every time as I said, I may forget to tell you to take a screenshot. Just give me a moment. Let's take this to the top. Okay, so you can take a screenshot of this. If I forget, please do take. Okay. I might suddenly in this thing, I might forget to tell you a screenshot, to take a screenshot. So please always do take it before I move on. Okay, so now we are talking about where on earth is this electricity generated that can cause this pitting. Okay, number 1, 2 dissimilar metals are there. Okay, your shaft and your bearing, there are 2 different metals. Okay, that is one thing. And whenever there are 2 different metals, there are larger chances of developing electrostatic energy. A second reason, and the more pertinent reason, is your ICCP is delivering that protective current to protect your particular ship's hull from getting rusted. Those electrons or those negative charges that are carriers of electricity, that protective current is flowing through the seawater. The seawater is acting as the electrolyte. Okay. And then, okay, 1 second. Let me draw that and show you. I'm not a very good artist, but this is your stern tube. Okay. And here's your shaft coming out. Okay. And here's your particular propeller. Okay. Now here is the ship's hull, here's your shaft. So one thing, as I said, two different metals. Okay. This is almost a pure stainless steel, your shaft. And this one is your normal iron and steel. So two different metals. Whenever there are two different metals and this one is turning, okay, there are always chances of electrostatic energy that is going to be building up. Secondly, okay. Secondly, as I said, your ICCP system is taking and pumping out that electricity. Those charges that are going to be preventing this very hull. Okay. Now, yes, it will be protecting all those areas that have become positive in nature, because we have to make our hull negative in nature, no? But what happens to the rest of those things? There are going to be still some spare electrical charges, and that they keep on building up over here. Why are they building up over here, especially at this particular point where your propeller is coming out through your stern tube? That is because over here, we are having it insulated. Okay, and how is it insulated? It is insulated by the lube oil, your stern tube oil. Okay, you're having your seals, you're having your stern tube oil that is preventing water and all that from getting into your engine room. So basically, you're having an insulation over here. But let's say this is the gap. Okay, let's say this is the gap. You're having a lot of charges over here. Plenty, plenty, plenty. Now this is building up, building up, building up, building up. Then it builds up so much that there is every possibility for it to arc across, because this one, through your main engine bearings, etc. Why main engine bearings? Is because the gap, this gap is larger. It will come over here, and between your main engine bearing, of course, you have an intermediate bearing also somewhere in between here. The gap of the intermediate bearing is quite large, so it is not going to go there. Remember, current always flows to the easiest part. So here your intermediate bearing will be having a gap this much, whereas your main engine bearing will be having a gap of this much. So obviously it's not going to go through this gap. It is going to be going through a closer gap over here. So current will flow down this through this gap of your main engine bearings to ground, and then cause your main engine bearing to get pitted. The main reason is because of your ICCP current, apart from your two different metals that cause electrostatic charge. Okay, so it's basically the current over here is causing this electrostatic charge to build up over here and suddenly arc over and flow down your shaft. And obviously current is going to be taking the shortest possible thing to earth. And that could be your main engine bearings. Okay, therefore, in order to avoid this particular, excuse me, to avoid this particular problem, we are having this thing called the shaft earthing. Somewhere around here, just before your intermediate bearing, over here, you have a slip ring. It's a certain metal, mostly stainless steel, which is wrapped around your shaft. And then you will have your brushes over here. Okay, your brushes. And those brushes are then taking it down and earthing. So the current, yes, the current will flow. This thing is still, your ICCP is working. You're not switching off your ICCP unless you're in port or the requirement arises that you have to shut down your ICCP. Till that time, it is developing this thing. Till that time, it is still developing these charges. Okay? And current will keep flowing, come up over here. Your brushes have to be making proper contact with the slip ring. The current is then going to be flowing in this particular manner. Okay? Through these slip rings and down to ground. Instead of going all the way towards the shaft, going through your main engine bearings, okay, and then going to ground. So by doing this, you are preventing your main engine bearing from getting pitted, and you are also preventing your main lube oil from getting contaminated, okay, or degraded. Okay. Right. So if you have taken the screenshot up till here, as you can see right at the bottom, I had mentioned about those two different metals. Okay. Technically, when two current carrying dissimilar metals are in contact, sparks, in other words, arcs, okay, travels at the point of contact, which erodes the metal by making a cavity called pitting. So where does that happen? That happens at your main engine bearing. So that is what is also called as spark erosion, which is basically arcing and pitting. Okay, so you can take this fully as one screenshot. Okay. So if you are going to search for a shaft earthing system manual on board, you will never find an individual one. Since it forms part and parcel of your ICCP system, you will find the manual in your ICCP system. This particular shaft earthing system consists of 3 brushes. Okay, these brushes are not carbon brushes. Yes, they do have carbon in them, but it is basically silver graphite. Graphite is carbon, and you have a silver component making it very hard in nature. But not so hard so as to act like a diamond. Diamond is one of the hardest substances or things on earth. Okay, that is why diamonds are used to cut several things, isn't it? But here, it is hard enough such that it does not wear down easily. Okay, these brushes have to be making proper contact. So suppose this is your particular shaft. Okay. Therefore, your brushes have to be making proper contact. Okay, this is not a perfect circle. Okay. And there is a third one also generally. Okay, these two are taken and given to directly to us so as to drain out the thing. Okay, this one is taken as the earth for your meter. Okay, let me redraw that. Okay, for your meter that you're going to be seeing. So it will be earth in that particular manner. Okay, so let's see how this is going to be working. We will see a video also on its operation. So if you're taking a screenshot of this, let me clear out this. We can take a proper screenshot and we'll see some photographs with regard to that. Okay, you can take a screenshot. So here's your shaft colored in yellow. It is coming out through your stern tube and connected to your propeller. Okay, and of course you'll be having your seals and the lube oil that is going to be preventing the seawater from entering. Okay, and here are your those two brushes over here of silver graphite, and a third one. The third one goes towards your meter. Okay, this is the junction box to the meter, and the other one is going directly to ground, to this particular thing. Ground meaning your particular plating. Okay. Right. So the propeller at the aft is a large area exposed metal which attracts protective cathodic current, which produces an arc while discharging from the lubricating film. Now the lubricating film, as I said, if the charge keeps on building and building, then even through your lubricating film, which initially was acting as a insulating material, will arc over. Okay, this results in spark erosion because the current, if this was not here, that was, current would travel down the shaft and cause spark erosion, in other words, pitting of your main engine bearings, which can lead to worse situation if lube oil somehow gets contaminated with seawater. Okay, so you will have the same lube oil over here for your stern tube. Both are one and the same lube oils. You are not going to be having a different lube oil for your stern tube. Okay, if this effect continues for a considerable amount of time, it may lead to overheating of the main engine bearings, caused by improper lubrication, resulted by cavities of the spark erosion. It may also lead to formation of oil mist, which would cause emergency shutdown of the engine, or in the extreme cases, a crankcase explosion. Okay, the very time that you get oil high mist alarm, first it is going to be thing, and then when it goes beyond a certain amount of time, then main engine shutdown is activated. Okay, is that clear? Any queries or doubts thus far? So always make certain that you are having spare brushes. Now these brushes are kept in place. As you can see, this is the brush holder. You can see part of the brush over there. They will be held in place by a holder. Let me zoom in sufficiently. Okay, can you see this? Okay, these are holding. This is a case through which your particular brush is kept in and held in place. But what is keeping it against this are these things which are spring loaded. Okay, you can't see this one, but they are spring loaded. Why are they spring loaded? It is so that due to the turning of your propeller, these things can jump out. Okay, because since this is a ring that is kept around the thing, there will be a cut in between, and every time the cut passes through, it will make this thing jump up. Okay, so that's why this is holding it down, but it should hold it down with a certain amount of pressure, not too much. If it is too much of pressure, they normally have 3 settings: light, medium, and heavy pressure. If you're going to put it on the third most thing, it's going to press down fully onto these brushes, and your silver graphite brushes can get worn out very, very rapidly. If you put it too light, then this sometimes may or may not make contact, in which case you're not having adequate protection. So generally it is kept in the middle. Okay, so that sufficient pressure is enacted on these brushes, 1, 2, and 3, so that you get proper reading. Okay. Now you can see that there is a meter over here. Every morning we take the readings. Okay. And the reading on the meter should be in the green portion. Okay, generally, I'm not saying every time it is between 5 and 30 milliamps. Each manufacturer will have different specifications. Some I've seen up to 80 milliamps. Okay, so if you go beyond that 80 milliamps, and in this case, beyond 50 milliamps, that means your particular brushes are dirty. So you'll have to clean it. Normally, this is part and parcel of your Saturday routine. Yes, you may be out at sea, but make very, very certain that especially these two brushes, at least one brush is making. Don't take out both and clean them. Be very careful, because if your finger gets caught here, your fingers are gone. Remember, your shaft is turning at a relatively high speed. When I say relatively, it's high enough so that you can also damage yourself. Okay. So be very careful. One at a time, remove. This one says it's going to the meter, has no effect on the system, because it is only giving for the indication, is giving the ground path for the indication. But these, at least one of them has to be in circuit at all times. Because if you remove that, the current is going to go down your shaft and damage your main engine bearings. Okay, just that instant is more than enough. Okay, clean this. Okay, we'll see the maintenance now. Okay, first we'll take the reasons for the spark erosion, then we'll see the maintenance. Okay, so why will we get the pitting or spark erosion as it is called? Shaft earthing arrangement is not working properly, as I mentioned on one of my ships that happened, and that is why they ran into such huge problems. Okay, although the brushes were in place, they had worn down quite a bit. And if they wear down quite a bit, despite putting it even on the third one, it is not going to be pressing against that particular ring, the slip ring. Okay. Cathodic protection current is wrong. Okay, so suppose your thing has been put in the manual thing and you're giving a very high current, not only would it damage your particular paint of the hull paint of your ship and cause more rusting to occur, this extra current will cause more current to be flowing down, and that may not be sufficient. Okay, your particular this thing may not be sufficient to bypass it. Maybe your brushes also again might be a part of your problem. So cathodic protection current needs to be always correct. Okay, the hull coating is excessive than required, which will increase the galvanic corrosion of the shaft. Galvanic is the galvanic action is because of two different metals. We saw that. Okay. Slip rings and brushes in the earthing device are worn down, therefore not making proper contact and not draining away the current, this electrostatic current. Okay, and the contact between shaft and earth device is not clean. Okay, so you require to have that particular maintenance. Okay, so if you have to order for it, what the brushes, or even for that matter the slip ring, okay, you will find it in the manual somewhere towards the end of the ICCP manual. Okay, and as you can see here, just one moment, let me zoom in. Okay, so item number 4, silver graphite brushes that are in use, 3. So always have 3 in use. Oh, sorry, as spare. Okay, so that at some point in time, when it needs to be changed, you are not left wanting. Okay, for that spare. Always keep the spare ready. Maintenance and service, as I said, it's a weekly routine. You should include it in your Saturday routines. Be very careful when you're this thing. Number 2, if there has been a buildup of oil or carbon from brushes on the slip ring face, this should be removed with a degreaser and a soft cloth. Never use your emery paper, because you can damage the surface of that ring. Okay, point 3, inspect and clean the brushes and brush holder to allow free movement. Okay, so you'll be having your silver graphite dust and all that. Please make sure that all that is cleaned. Okay, inspect the brush copper pigtails. What is this so-called pigtail? Okay, let's go back to this diagram. Can you see? Let me zoom in more. Can you see these copper wires like a braided wire? Okay, coming from the brush, and then it's connected here. This one is also coming from the brush and it's connected here. Cannot see this one so clearly, but yes, it is connected somewhere here. This is the thing. Since it's against a background, you can't make it out. These are called pigtails. So, suppose this is your brush. Okay, suppose this is your brush. Then to that is this thing. Generally, you're going to have either these lugs, either the U-shaped or the round one, and then you'll be connecting it over here. This particular thing here is the pigtail. Okay, why is it called a pigtail? That is why I drew it in a curly fashion, because when you're going to think, it is going to be curled up like this. You can try and straighten it, it's going to come back into this position. That is why it is called a pigtail. And if you see a pig's tail, it is going to look exactly like this, okay? So, with regard to the pig's tail or pigtails, those things can sometimes get eroded and can be very thin down, and thus those few strands will not be giving you a proper conductive current for your earthing to go down to ground. Okay, so see that they are also in good condition. If not, replace it. Your brush may not have worn down, but because of this thing can also cause this particular spark erosion or your particular pitting in your main engine bearings. Okay, such a simple reason. Okay, the brush wear down should be noted, and the compression of the hold down spring of the brushes should be adjusted to ensure good electrical contact with the shaft ring. If excessive wear is noted, check the brush spring tension, as it may be excessive. Okay, as I said, there are 3 settings, one low, one medium, one high. So generally, whenever you are first putting your brush into place, it's a brand new brush, then generally you put it into the high, okay, so that it takes the shape of your particular shaft. After that, you put it into medium. You put it in low because of the brand new brush. What is going to happen? It may not be exerting enough force for it to touch the shaft. Okay. Right? So let me zoom out a bit so you can take all the maintenance. This thing. Okay, you can take a screenshot of this. Number 5, a millivolt reading of 0 when the shaft is turning out at sea. Now, if your shaft earthing is working properly, you will get some reading, right? And as I said, suppose this is your shaft meter. Okay. And what they've got an indication is up to here is red. And then you have a green section. And then you have once again a red section. Okay. So this particular red section is less than 5. It can vary from ship to ship, manufacturer to manufacturer. Okay. Basically, it is manufacturer to manufacturer, but this is the general thing. Okay. And this green is between greater than 5 up to 30 MA. 1 minute. Let me go up a little bit. 30 MA. Okay. This red portion is less than 5 MA. The green portion is greater than 5, but less than or equal to 30 MA. Okay. Up to 50 MA is acceptable. But if you go beyond 50 MA, that means your brushes and all that are dirty. Okay. Now, why are we talking about 50 MA, 80 MA? Is because the current is not flowing directly to earth. Why are we having that current not flowing directly to earth? Is because this static electricity. So now we saw that particular, this thing over here, no, your stern tube. Let's go back to that. That will be easier to think. Okay. So if this is dirty, which these two, remember this brush for your meter is totally different. It's not got nothing to do with this. Okay, so what is happening if this has got dirty? That means what? Your charges and all that are building up over here, no? And then they are discharging now due to the arcing over of that insulating medium, your lube oil flowing here. Now it is supposed to flow through this to earth. Okay, it is supposed to go like this to earth. But it is not. So therefore, this voltage, if you're going to take your meter and connect over here, black test rod, sorry, let's make it the other way around, and your red test rod to this, okay, then it will be showing quite a voltage. Okay, quite a voltage it is going to be showing. So this, I'm sorry, this meter over here is not milliamps, it is in millivolts, okay? So this voltage is going to be pretty high. So it will be probably reading somewhere here, okay? Because of this development of thing, it is not going through that to ground. So if it was going through ground, then obviously this particular voltage is going to drop well below that. It should not be zero for the simple reason is your lube oil is acting as an insulation, and it should not be zero whenever your ship is in motion, because there will be sufficient of lubrication oil here and sufficient of lubrication over here, and due to the proper earthing, this charge is definitely going to be going down to ground, giving a minimum voltage reading over here. Okay, and that minimum voltage reading should be anything between this green portion. Okay, if it is showing zero during your particular thing running, okay, we'll see that now. Okay, if the millivolt meter is reading zero when the shaft is turning out at sea, it indicates a 40 millivolt meter, or there might be a break in the line. Okay, so going back to this particular thing, either this one is gone kaput, or the connection between here and here has gone kaput, or your particular earthing here for this meter is not making properly. Okay, so check the other way around. Don't directly assume your meter is faulty. Check all the connection. Maybe the connection inside, the earthing connection inside has gone. Okay, has slipped out or something like that. Okay, lastly, you will be able to come to the conclusion that your meter has gone kaput. Okay. Okay, and point number 6, the effect of spark erosion will be minimum if the potential difference is below 50 millivolts, but greater than 5 millivolts up to 30 millivolts is the best. That is for this particular thing where I have taken from the manual. Okay. Ship to ship, it will vary. And when I say vary, manufacturer to manufacturer. Okay, and all the ships are not going to be having the very same thing. Okay. Is everybody clear? Any queries or doubts on your shaft earthing and why it is so important that it is working properly? Okay, so let's see a short video on this with the working of your okay.
Sir, is there any?
What?
There is no audio, sir.
So we are not able to hear any audio on this.
Not hearing audio. It's only music playing here. There's only music playing.
Okay, sir. Okay.
So it doesn't matter. Okay, so that video was only having music playing. I forgot to share that with you. Share it properly rather. But I hope you got the gist of what we did. Okay. So any queries or doubts on your shaft earthing? Okay, so let us now move on to another topic, and that topic is transformers. Okay, so you can take a screenshot of this. What is the definition of a transformer? Okay, a transformer is a static device. Static means stationary. We saw the static AVR, no? Okay, stationary means it's not moving. Okay, nothing is moving in that. You have your primary, you have your secondary, and you have your core. None of these are moving. Even in your auto transformer, you're having a winding and you're having the core. Okay? Nothing is moving over here. Okay? So that is the moving, that's the meaning of static device. So a transformer is a static device or equipment that transfers electrical energy from one circuit to another by means of electromagnetic induction. The moment you talk about electromagnetic induction, Faraday's laws of electromagnetic induction comes into play. Okay? And the main thing in this is that whatever the input frequency to your primary, you will get the same input frequency at your secondary, at the output. Okay? Whatever the input frequency, that same frequency is going to be there. That is because of electromagnetic induction, Faraday's laws. Faraday's laws, one of its states is only if you have a changing electromagnetic field. And that electromagnetic field is going to be at 60 hertz. So because of that, a voltage is going to be induced in that. And because that voltage is induced due to this changing electromagnetic field, it stands to reason that your secondary also will be of 60 hertz. Only the voltage will change. And current also. If it is a step-up voltage, then current will fall. If it is step-down voltage, then current will increase. Very easy to understand that why voltage and current have a relationship because of the power. Power is equal to V into I. Okay, so we are having a certain power transformer. Then that power has to remain constant. It cannot change. Okay, so for a given transformer, a given power for a transformer, V into I, if V is increasing, then I has to decrease. And vice versa. If voltage is decreasing, current has to increase. Okay. So what are the uses of this transformer? As you can see here, which are listed. Okay. Used as a step-up or step-down transformer. With regard to voltage, you can either step up the voltage, you can step down the voltage. Okay, and how do you step it up? By having more number of turns. We'll see the ratio of the turns and the voltage. Number two, used as a means of isolating or direct connection. We spoke about something called as buffer transformer. Just give me a moment. Let me zoom in so that you can get a proper screenshot. Okay, so you can take a proper screenshot of this. Okay, one very good example is whenever we electrical officers have insulation fault, say coming in washing rooms, okay, the laundries, crew or officers' laundry. Okay, you've tried your level best and that particular thing is within the circuitry. So obviously to change the circuitry, that's going to cost a bit of money. And the company, if you ask the company, they say, we don't have the budget to change the washing machines. Okay, ask Bati Sahab to somehow or the other try and mitigate this problem. And then that next port, you're going to be having a wetting or a PSC inspection or whatever inspection. Okay, so obviously you have to mitigate that insulation fault because it is showing on the MSB. So what do? Definitely we have some buffering transformers or isolating transformers. So you'll have the same number of turns in the primary as that of your secondary. So if it is 220 volts over here, you will have 220 volts also over here. But whatever the earthing fault that is over here is not, this is in the primary. Whatever earthing fault that is here, okay, in your secondary is not reflected into your primary. You have buffered it or you have isolated it. And such transformers are normally called isolating transformers, where your voltage and current are going to be the same in your primary and secondary. So you can also use your secondary as a primary. You can interchange the connections. Nothing is going to happen. Okay. Point number 3, from one above, also used for auto transformer motor starter. We saw in the motor starters, where the auto transformer is consisting of only a single winding. Okay, and depending on if you are wanting a step up, then the primary will have less windings, in this case like this, and your secondary will be the entire winding. Conversely, if you want your step down, then this becomes the secondary and this one will become the primary. Okay. Now, if you remember when we were doing the power thing about your alternators, etc., we said that the manufacturer will never be able to give you a KW rated equipment. We saw what Ankit sir was discussing the other day, that beer mug. You have bought that particular 1 pint of beer, and that guy has opened the beer tap, he's filled up your beer glass, and then this part, okay, let's give a very rough diagram. Okay, so this is your beer mug. Okay, so one part will definitely have sufficient of amount of beer. Okay, but at the top over here is the froth. And yes, he tries to fill it up as much as possible to give you your money's worth, but there's still some gap over there. In other words, this is the real power. This here is the kVAR or wasted power, and this here, the entire thing, is the kVA. And this kVAR, the wasted power, will depend on what is the load that particular generator, and in this case, this particular transformer is going to be connected to. Okay, so the manufacturer who is manufacturing your alternators, or the manufacturer that is manufacturing your transformer, he does not know what type of load his particular equipment is going to be connected to. Where you're going to get KW right at the top, that's never ever going to happen. Try as that bartender wants, he is not going to be able to think, unless he throws out all the froth and keeps topping it up, then throwing out the froth, topping it up, keeping on throwing out the froth. Then he'll be only doing that, and he will not be able to attend to the other customers. Plus, that bar needs to make some money also, no? Right? So they will never ever give you a thing that is completely topped up with only beer and no froth. Okay? It is something very similar to that. So always your transformers, always your alternators will be rated in kVA and not kW. Okay? You might have definitely ordered a transformer on board your ship for something or the other, whether it's step down, or even your isolating transformer. Have you noticed in your particular ISA or IMPA code book, they give the ratings in kVA, not kW. So 1000 kVA would mean 1000 kVA, not kW. kW, the actual rating is actually much less. Okay, much less than that. You can say almost 20% less than the kV. Okay. So if you are always having a doubt, always go for a higher kVA. If you don't know what is the power that is required, always go better for the higher kVA. Okay. Is that clear? Any queries or doubts thus far? Has everybody taken a screenshot of this? Let me clear it up so you can take a proper screenshot then. Okay. Let's see the principal parts of the transformer now. You can take a screenshot of this, then we'll see. The principal parts of the transformer are number one, core. Okay. And of course, your windings. Now, your core consists generally of two types, hollow and shell type. But first and foremost, why are we having a core? What is the reason, or what is the core first and foremost made of? Okay, as you can see, the core is generally made of soft iron or cold steel, but you can also have air. That means use a material that is non-magnetic in nature. Okay, so here you are going to have your transformer. This is your primary. You're given a AC source. And you are going to have, let's say, a step-down transformer over here. Okay. Let's say this is having an air core. That means no soft iron core, no magnetizing material. And this one will be having its electromagnetic lines of force, which will intercept your secondary. But the problem with this one is not all these electromagnetic lines of force are intercepting the secondary. So there is a very great possibility that the voltage that you want induced into your secondary may not be correct in a air core. Therefore, mostly you will have soft iron core, and generally that is always indicated in that particular thing with these two parallel lines. Okay, now why are we sometimes we still use air cores, but as I said, we also use the soft iron core. The soft iron core is okay if your frequencies are lower, so a frequency of equal to or less than 20 kilohertz is okay. And we'll see the reason with regard to your iron cores. But what happens is if the problem of your frequency becomes greater then 20 kilohertz. We've seen in the high voltage section, when we did the high voltage, we saw something called skin effect, no? Why was the skin effect occurring? And it had nothing to do with the voltage. As I said, it was for high voltage, it was for low voltage also. What was the common denominator between that high voltage and the low voltage? Is that our frequency is at 60 hertz, no? So no matter what the frequency, that is at 60 hertz. Now we are talking about 20 kilohertz greater than or less than, and 60 hertz is certainly less than 20 kilohertz. That is why we are using a soft iron core, because we are using 60 hertz. But what happens when we are having a frequency? Changing electromagnetic lines of force. Changing electromagnetic lines of force are going to cause that soft iron core to get magnetized. It is made of iron and steel, isn't it, that core? So that particular core will be having a lot of tiny, tiny magnets. Okay? Tiny, tiny magnets. They are going to be all in different, all scattered around like this. North, south, north, south, north, south. Okay? Like this. There will be various things. So it's not going to be magnetized. But when you're going to be giving this, then these will all get magnetized in a certain direction. All north to one side, all south to one side. Okay? North, south, all south to one side, all north to one side. So it gets magnetized. And when it gets magnetized, due to this changing electromagnetic field, a current is going to be induced into this soft iron core. And it will cause losses. And we will see what those losses are once we see what are the types of soft iron cores we are using. Okay? So what are the cores that we are using? We are using the hollow type core and the shell type of core. Let's see the shell type of core first. Okay? Sorry, the hollow type of core first. The hollow type of core is shaped such that the laminations have a hollow in the center and the respective windings are on either side. Okay, let me zoom in a bit so that you can take a proper screenshot. No, it's too much. Okay, so you can take a screenshot of this. This is the hollow type of soft iron core. We will come to the reason why we are having it like this. It is not a solid block with the center hollowed out. Instead, that block is cut into very thin slices. It is hollowed out and then cut into very thin slices of that same material, okay, soft iron or steel. And then each of these slices is given an insulation. So it is dipped in varnish. Okay. So the hollow core is shaped such that lamination has a hollow in the center and the windings. So possibly this is the primary winding and this is the secondary winding. Okay. And remember, if the secondary winding is a step down, the current will be higher. So here they are shown, probably this is a step down because thicker windings, more current. Okay? Everybody clear thus far?
Okay, sir.
Let's go to the shell type. Okay, let me zoom out a wee bit so we can get the relationship between the current and the turns also. Okay, so the shell type, as you can see here, consists of those same laminations. That means it is not a solid block. It is again cut into very thin slices, and each of those slices are insulated from each other. The difference between the shell type of core and the hollow type of core is that this one has E's and I's. You can very distinctly make out that this is an I section and this is an E section. They are all separated from each other. Okay, you can take away the I section and you have take away the E section. Both are separate from each other, but they are formed in such a way that when they are put together, it looks like this. Then instead, and of course, each of these slices are going to be insulated from each other exactly in the way the soft iron, the hollow soft iron core was done. Each of these I's, each of these E's are going to be insulated from each other. Okay? And your secondary and primary are wound on the central section of the E. Not one here and one here. Because then this part is going to interfere with the electromagnetic lines of force. And generally, your primary is wound first. So you can see the lighter portion over here. And the secondary is wound on top. Okay. So this is your shell type of soft iron core. What is the relationship between the voltage and turns? Generally, in the writtens, they will ask you, they'll give you a problem and to solve. So you'll have to know that you're having a direct relationship of voltage and turns. More the number of turns, more the number of, higher is the voltage. So if the number of turns in your primary are more than that of your secondary, then it becomes a step down transformer. If the number of turns in your secondary is more than that of your primary, then it becomes a step up transformer. Okay, so the direct relationship V1 divided by V2 is equal to N1 divided by N2. Okay, and now the relationship between the current and the turns. So I'm going to keep both these together so that you can take it as one screenshot. Okay. The current is inversely proportional to the number of turns. For the simple reason, as I said, the power of your transformer is going to remain the same. It's not going to be changing. P is equal to V into I. So if V is going to increase, current has to decrease. And if V is going to decrease, the current is proportionately going to increase. And therefore, if you're going to put all of them together, so V1 divided by V2 is equal to N1 divided by N2 is equal to what? I2 divided by I1. Is that right? Correct or no?
Yes, sir.
Okay, generally they don't ask you, but you can never say never. They can always tell you, okay, if my number of turns in your this thing is so much, what, and this is the voltage, what is the current of your transform? Okay, so always be prepared for the thing which you are not expecting. Okay, they can always ask you. As I said, what is asked in the orals can be asked in the writtens and vice versa. Okay, let me try and get this entire thing for you. See if it is too much. Okay. Okay, you can take a screenshot over here. So as we saw, the greater number of turns in the secondary than the primary, your voltage would be stepped up, but your current would be stepped down. And vice versa, if the number of turns in your primary is greater than your secondary, then it will become a step down transformer where your voltage is stepped down. But obviously the current is stepped up. Okay, and so therefore point number 2 from those formulas, voltage is stepped up, then current is stepped down. And if voltage is stepped down, the current is stepped up. Okay. Okay, one little out of the way question is asked. It is a very commonsensical answer for this. So if this question is asked, what would happen if the primary of a supplied voltage and the secondary winding is left open? So in other words, you have, for example, that same buffering transformer, 220 volts, you have connected it over here, and you have taken that washing machine, you disconnected it off over here, but you've forgotten to take out the connection from this side. This is the supply. Okay, you've forgotten to disconnect it from the supply. So what would happen if the secondary winding is left open? That is, it is not connected to the load. You've taken out the washing machine. Okay. Generally, the plug and all that would be over there. It is plugged in. You forgot to switch that particular plug source to the off position. So if it is left like this, AC voltage causes a small current to flow. Okay. This is going to be connected over here in the form of your electromagnetic lines of force. Voltage is going to be induced. And as I said, this is an isolating transformer. So 220 volts is going to be induced into that. So you will be having a live voltage over here. No current is going to be flowing. But the moment somebody touches here or you touch over here, you are making a path through yourself. So current is going to be flowing through here and you will get quite a nasty shock. Okay. So that is one of those things that could happen if your primary is given the supply and your secondary is left open. A second thing happens. Your primary will get burnt out. Not immediately, but over a certain period of time, may not be 1 hour, may not be 2 hours, but certainly after 5 or 6 hours, this is gone. The primary is opened up. Why is that? And if you touch the particular transformer at that time, it would be boiling hot, very hot, especially the metal which is over there. And you, when you go there near to it also, you will feel the heat, you will even get the burning smell also. Why did your secondary is open? You just kept it open. So nothing is definitely going to happen to your secondary, but certainly your primary is going to be burnt out if it is connected to the supply and this is kept open, the secondary is kept open. What happens? Electromagnetic lines of force are going to intercept the secondary. That is going to be inducing a voltage over here. if there was a load, then you're going to have a current flowing. Okay? If there was a load connected, as earlier, there would be a current flowing. And when current flows, this is also going to be having its electromagnetic lines of force due to this particular current flow. These electromagnetic lines of force that are caused by your secondary, when it is connected to the load, those electromagnetic lines of force are going to be changing at the same frequency as your primary. Those electromagnetic lines of force are going to again cut your primary windings. And when it is going to cut your primary windings, you are going to get a voltage induced into your primary called back EMF. Okay? Voltage is going to be induced back into your primary called back EMF, and because of this back EMF, you are going to get a current flow. That current flow is going to oppose the original current flow flowing through your primary. Remember, this is a continuous circuit. Your supply is giving voltage and current is also flowing. Now, this back EMF is going to be in this particular manner induced into your back into your primary, which is going to cause a reverse current flow that is going to oppose your initial supply current flow. And it is going to keep your current flow limited such that your primary doesn't get overheated. It is going to limit your supply current flow to a safe value such that your primary doesn't get overheated and burn out. But now you have kept it open. Okay, you have kept it open. Voltage is induced over here, but now there's no load. So where is the current? There is no current flowing now. It is an open circuit. With the result, there is no back EMF created. Since there is no back EMF created sent into your primary, there's not going to be any of those opposing current flow. In other words, the supply current is going to have a free for all. It's going to increase tremendously. And when the primary current is going to increase tremendously, remember, if the current is increasing, so also would the heat dissipated also increase. That keeps on heating and heating and heating up to such an extent. And remember, any device, when it goes beyond its normal operating temperature by 10 degrees, then the insulation falls by 50%, 50%. So here the current is going to be flowing in your primary is so high that within not hours, maybe minutes, okay, maybe 30 minutes, maybe 40 minutes, and your primary is gone, is going to be burnt out. And whenever you go to such a situation and you go and stand near that transformer, you will get a terribly burning smell. It's happened several times even to me, not on the transformer, but to solenoid relays, solenoid coils.
Sir, can you please repeat again?
Repeat what?
When we keep open, then why the current is increasing and increasing?
Okay. Now let's take the condition when your washing machine. We were talking about the washing machine, okay, and using a particular. So this is your washing machine. Let's call it WM. Okay. So you have connected this isolating transformer. So you have 220 volts as the supply in your primary. You have 220 volts supply in your secondary, because winding number of turns in both are the same. I'm taking this very simple example, not step up, step down. We are not interested in that. Okay. So whatever the current that is flowing over here, because the load is connected over here, you will get that same current flowing in your secondary. Okay. And when there's a current flowing in your secondary, remember that you're going to have an AC, no, which is at 60 hertz. So because of the changing because of this changing current due to having an AC over here in the secondary. This one also, due to this current flow, this also will develop its electromagnetic lines of force. And these electromagnetic lines of force, due to the iron core, soft iron core that we are using, will cut your primary. So primary is inducing a voltage in your secondary, but now due to the current flowing, the secondary is inducing a voltage back into the primary, called back EMF. That's why it's called back EMF. Okay, and when it's going to be inducing a voltage back into your secondary, a current is going to be flowing in the primary that is going to oppose the original current. So if the original current was flowing in this direction, okay, now the current is going to be flowing in this direction. Okay, so you'll have the original current flowing as shown in red. That by this one is going to be shown as in purple. They are going to be opposing each other. Okay, they will oppose each other and cancel out. Not fully. In other words, the current that is going to be flowing as shown in purple, that is not going to be as much as the current that is going to be flowing in red. So it is limiting your supply current to a safe value such that your transformer does not get heated and it does not burn out. But what is happening now? Suppose you have taken that washing machine down to your workshop. What you forgot to do is you forgot to disconnect the plug from your supply, and also that switch is in the on position from that plug. So you're getting supply to your primary. You left this open, no matter, okay, suppose you have not insulated these ends, then yes, you will get a shock. But let's say you even insulated this. Okay, because of the changing electromagnetic lines of force in your primary, voltage is induced into your secondary. So if you take off that insulation material, connect your voltmeter, you are going to get 220 volts. Okay, so then you put that insulation material back, and then again you've forgotten to switch off this. Then in the same case, this secondary is open. So that current that was flowing initially when you had your washing machine connected, that current is absent. When that current is absent, this electromagnetic lines of force by your secondary will be absent. In other words, you're not going to be having a back EMF. And when you don't have a back EMF, this current is going to be also absent. So what you're going to get, you are going to get an increased current flow. Okay, an increased current flow in your primary, because there's nothing going to oppose it now. Okay, because of this increased current flow, the heat in your primary is going to be quite high. And as we know, if the operating temperature is increased by 10 degrees over the normal operating temperature, your life, the insulation life, falls by 50%. And very quickly, your transformer primary will get burnt out. Is that clear now? Okay, that same point is in point B here, write down. Okay. Impedance of the primary is quite low, and if the current is allowed to flow continuously with the secondary open, the secondary induces a counter voltage or a back EMF, as I called it, into the primary that keeps the primary current in check. So a back EMF causes a counter current. Okay, and then this current can damage the primary winding due to that particular thing. So if that back EMF or counter EMF is absent, so also would be the counter current. And your primary current will have a full field to play with, whereby you are going to increase, or the primary current is going to increase to such an extent that the primary windings would get overheated and finally burn out. Okay? Is that clear?
Sir,
Yeah.
only this isolating transformer like this happen, or step down transformer also?
I've just taken this as an example. Okay, I've just given it to you as you can have it step up, you can have it step down. अगर ये छोड़ेगा ना ऐसा खुला तो जाएगी ही जाएगा तुम्हारा प्राइमरी जाने वाला है definitely. I've only taken this as an example because I said if you're taking you had a faulty washing machine वो नीचे लेके गया अपने workshop पे और ये खुला छोड़ दिया. Okay, I'm just taking this as an example. So not necessarily a buffering or isolating transformer. It can be any transformer that if you keep your secondary open circuit, तुम्हारा primary जाने वाली है. Okay.
Okay, sir.
So that's why I said even I have made this mistake not with a transformer but with a solenoid coil. Okay, your solenoid coil has a coil outside and then you have that core inside, no, which either opens or closes a valve. है कि नहीं? So that
Yes,
is
sir.
acting as the secondary. अगर वो the coil, the solenoid, the core, if you take out, तुम्हारा primary में कुछ नहीं आता है ना. It's not going to be doing that. So the same thing, and that your coil is going to get burnt out. Okay, this happened long ago when in the olden days we never used to have PLCs for your purifiers. We used to have what was called as the operating water tank. There was a tank of water, and that tank used to the water in that tank used to give for lifting your bowl for discharging. Okay, so you had your solenoid valves for that. एक दफा क्या हुआ कि मैंने just to take and try and put a like a sort of a thing for that diaphragm, that thing for your core. मैंने वो core निकाल के and I left the coil aside. Supply was still being given. बाद में आके देखा कि coil इतना गर्म हो गया and definitely I got a burning smell. That coil was burnt out. Luckily we had a spare. Okay, otherwise we would not be able to use that purifier. Okay. So whether it is a transformer, whether it is your solenoid coil, please do not make the mistake of taking out the core of your solenoid and keeping your solenoid connected to the power supply. You are definitely going to have a burnout of the solenoid coil. Okay, same principle, same reason. Right, so let's move forward. With regard to, we spoke about losses, okay? And we said that the core will also cause a loss. So before that, let's take a screenshot of what are current transformers, what are potential transformers. As you can see here, this one is a current transformer whereby you will be having as the primary one of your bus bars. And then you would have seen a brown donut shaped thing which is passing around it. You will have your bus bar passing as shown here in green, and around that is your other winding. So yes, really speaking, this is going to be a current transformer, or rather a voltage transformer, where the primary, which is the bus bar, the green thing, is going to act as the primary, and this particular one, which is on the donut shaped thing, is your secondary. But then, as I said, whenever voltage is induced into your secondary and it is connected to a load, in this case an ammeter, a current is going to be flowing now. Okay, so then this so-called voltmeter is then going to be calibrated for that current that is flowing in the second, and then it becomes an ammeter. Okay, so not only it becomes an ammeter, This particular type of thing is called a current transformer. Okay, so why go that far with regard to your ammeter and all that? Don't we have a clamp meter? We have seen the clamp meters, no? You can read voltage, you can read current on that. How? Same principle. Okay, you can read the voltage, you can read the current on that. Same principle is used. Okay. And your voltage transformers are always step down. Okay, you are never going to, that voltmeter that is going to be connected on your main switchboard is not going to be having 440 volts connected to the meter. It is going to be stepped down and then calibrated in such a way that it is going to read 440 volts. Because suppose you have to disconnect this meter, this side is live. And if you're going to have 440 volts on this side, you are exposing yourself to grave danger. Not only that, remember we said what is the safe working distance? It was about 0.6 meters. I'm not sure. Just give me a moment. Let me go back to that. Let me see what is the safe working distance for. Your 440 volts. Okay, so let's see what is the safe working distance for about 440 volts. Okay. This is for your this thing, 1 minute. So up to 1000 volts, greater than 1000 volts was high voltage, 0.7 meters. Even if you want to say as half a meter, if you put your hand very close to this, you are certainly going to have an arcing and you will get electrocuted. Okay, because it's going to jump across to you because you are the ground, isn't it? Because you're grounded through your shoes, even though you're having safety shoes with rubber soles. Okay, so you will be having that. Okay, so let's see that over here now. Okay, so if you're going to have 440 over here, then you are certainly going to be electrocuted in case you're going to want to change your voltmeter, which might have gone kaput. So a potential transformer, especially with the instruments on your particular, that's why it's called here instrument transformers. So for your voltmeter on your MSB, it is always going to be a step down transformer. And accordingly, whatever the voltage over here will be calibrated to give you a 440 volt reading, even though it is a step down transformer. Okay. Right. Let's now come to the losses. I hope you are taking a screenshot of this. Okay. Let's come to the transformer losses. So you can take a screenshot of what is copper loss, or also called as I squared R losses. Now your transformer is a fairly efficient device. You can have up to 98% efficiency, depending on what materials you're using for the core, etc., etc. But it is never 100%. As even Ankit sir was describing yesterday, if you ever get something that is 100% efficient, then this world would have been a different place. So you will never get anything that is working 100% efficiently. There will be always some loss or the other. So what are these transformer losses that are not even making it come to 100% efficiency? One of them is copper loss. Okay. Now, we spoke about copper being a conductor of electricity. We spoke about silver being a conductor of electricity. We spoke about aluminium being a conductor of electricity. Why are we using copper instead of aluminium? Aluminium is a conductor of electricity, copper is a conductor of electricity. But we are using copper in preference to aluminium is because the number of electrons carried by aluminium is less than that of your copper. In other words, the flow of electrons is not as much as the flow of electrons in your copper. Likewise, if you compare copper with silver, silver is a better conductor of electricity than copper. So, similarly, the number of electrons carried by your copper conductors is much less than that of your silver. But for obvious reasons, we are not using silver because the cost goes very, very high. So we make do with copper, and we do have copper losses. Okay, that is why even on our ships also, we are not having 100% efficiency. Yesterday, Ankit sir was talking about the power triangle. If there was 100% efficiency, then your kVA would land on your kWA. So you'll get all the power that is generated by your particular generator being delivered to the load. There would be no loss. Perfect. But nothing is perfect, unfortunately. So what happens over here? Because of this less flow of electrons, in other words, there is a sort of an opposition to the flow of these electrons. In other words, each particular conductor will be having its own internal resistance, the resistivity. Resistivity is the opposition to the flow of these electrons or the current carriers. Okay, and whenever you are having this particular resistance to this flow of electrons, that resistance is going to develop heat, and that heat is a loss. It is wasted energy, the kVAR. Okay, that is why we are having that kVAR. Okay, there is current flowing back and forth to the generator that is not being used. That is a loss. The heat that is produced due to this particular opposition to the flow of electrons or current carriers, that is also heat. That is also a loss. Okay. So because it is copper we are talking about, it is also called copper losses. But why is it called I squared R loss? The more current that is going to be forced to flow through that, the more opposition it is going to be facing due to that resistivity formula. Okay, let's assume we have not increased the cross-sectional area. Okay, the length more or less is the same. But if you are going to increase the current, then the heat produced is also going to increase. So that is why it is also called as I squared R loss. So copper loss or I squared R loss is still one and the same thing. Okay, so to reduce this, we have the cross-sectional area. Okay, we know resistivity directly varies as length divided by the cross-sectional area. So what are we going to do to reduce this loss? We increase the cross-sectional area so that this opposition to the flow of electrons called resistivity would form. Okay, but then again, we saw that we cannot use this too much, because if you are going to have cross-sectional area much larger, we can land up with skin effect. Okay. And that is also a loss. That also results in heat development, and that will finally also add up to the losses. So we have to have it in such a way that the cross-sectional area is just sufficient so as to keep those losses. There will be copper losses, there will be I squared R losses, no question about that, but it will be reduced. Okay, if you're going to increase the cross-sectional area within a certain limit. Okay, all clear? What is the copper loss or I squared R loss and why it happens? Okay, we'll discuss the eddy current loss. So if you've taken a screenshot, let me get everything in one thing. So we get copper loss, eddy current loss, and hysteresis loss together. And tomorrow we will discuss both eddy current loss and hysteresis loss again. Okay, please take a screenshot of this. And then I'll try and complete eddy current loss today. Okay, I'm zooming in now. Let's talk about eddy current loss. Remember, I said that if you are having your particular primary and your secondary with air, then the number of lines, electromagnetic lines of force that will be cutting your secondary may not be sufficient or may not be strong enough to induce the correct voltage in your secondary. Therefore, what do? They put a soft iron core in between. Okay, and then your particular electromagnetic lines of force will strongly cut your particular secondary. Okay, so why are we having a soft iron core? I told you that it is made of a ferromagnetic material. In other words, you are going to be having tiny magnets in this, and they are all going to get arranged in such a way that they will concentrate the electromagnetic lines of force of the primary such that it intercepts your secondary properly. Okay, but being a soft iron core, not only will your primary induce your voltage into your secondary, it will induce a voltage in this soft iron core as well. So your soft iron core is helping the electromagnetic lines of force to properly induce a voltage into your secondary winding by concentrating those electromagnetic lines of force. But what it is also doing is that it is allowing the electromagnetic lines of force to induce a voltage into itself. And just as we saw earlier, whenever a voltage is induced in something, a current is going to flow. And when a current is going to be flowing in this soft iron core, then it will also produce currents. And in this case, it's going to be producing a current that is called an eddy current. Okay? These eddy currents will heat up the core. Not only will it heat up the core, it is going to oppose the original electromagnetic lines of force. If you remember the sensors when we spoke about the proximity, the electromagnetic proximity switch or the proximity sensor, if we brought a metal, voltage was induced into the metal by the sensor, okay, and currents were going to be flowing in that metal, that would cause eddy currents that would oppose the original electromagnetic lines of force. So whilst you're using the core to help induce voltage or concentrate the electromagnetic lines of force, here you're also inducing something that is going to oppose the electromagnetic lines of force. all because of these eddy currents. So it is called an eddy current loss. Also, because you are using a soft iron core, it is also called as iron core losses. So tomorrow again, we'll discuss this and we will see how we are going to be reducing that. We saw those two cores, the hollow core and the shell type of cores. And what did I say? It is going to be sliced into very thin. You're not going to have a solid core here. It's not going to be a solid core. It is going to be in thin slices. Okay, everything will be thin slices. Okay, we'll see that again tomorrow. And each of these slices are then insulated from each other, preventing these eddy currents from flowing or reducing it to the barest minimum. And if you're going to have very less eddy currents, obviously it is not going to help in reducing the original electromagnetic lines of force. You will be having the proper thing being constant. It's not going to reduce the primary electromagnetic lines of force. On the contrary, it is concentrating it and helping it to be induced into your second. Okay, so that is what is eddy current loss or iron core loss. We'll again discuss this tomorrow so that you will be thorough in that. And then we will be doing hysteresis loss, the third loss, and all these losses put together. Okay, some of them you cannot mitigate, and copper and eddy current losses you can mitigate, but hysteresis loss you cannot mitigate. Okay, so we'll discuss that again tomorrow. Any other queries or doubts you have? Okay then, so we'll close our class here for today and we'll continue
Okay, thank you, sir.
on Monday then. Yeah, thank you.
Thank you, sir.
Welcome.